Right, so I'm going to present here the use of these two workflows with two studies, in motor noise and crossplay noise. And okay. So just a brief introduction to what am I doing. I did mechanical engineering in France, and then I worked for 5 years in France at Vitesco Technologies as an NVH engineer for electric motors. And recently, in January this year, I went to Lightyear, an amazing Dutch company. So I'm going to just shortly introduce Lightyear as well. And then I will present two study cases, motor noise and crossplay noise. So what is Lightyear? Lightyear is a startup. It was created 5 years ago by a group of 5 students from Eindhoven University. And they won, I think, 4 times the Solar Challenge in Australia. And they had this crazy idea to create a passenger vehicle from scratch. And I think it's a great success because this vehicle goes into production in a few weeks, and hopefully you will be able to see it next year on roads. So we want to deliver clean mobility everywhere to everyone. This is our mission. The Lightyear, the car itself has a lot of, I would say, innovative ideas, and the most important one is using the use of 4 in-wheel motors. So we don't have gearboxes, we don't have gears. It helps to get better efficiency. And there are a few other innovative things like very, very efficient inverters. And recently this car has the lowest drag coefficient on the market, so it's around 0.19. So let's move to the study cases, the in-wheel motor noise, and kudos go to 2 engineers from Actran, to Xavier and to Attila. They really helped a lot to develop these projects, and it's really amazing support from them. Yeah. So first of all, why do we even need to study NVH for electric motors? So there are 2 audio files, and I don't know how to play them.
What's next? No, you can use
this one. Okay. So one of them is good NVH performance, the other one is poor NVH performance.
Something unusual.
This one was good, and this one was developed by BMW engineers for the new generation of electric vehicles, and this one is not so good. So you can hear the motor, it's ramp up, and a certain rotation it hits some resonance frequencies in the structure, and it creates this annoying sound. So we would like to avoid this situation. We want to avoid these resonance frequencies, and in future, when we get rid of them, we can even think about creating like a brand signature sound of an electric motor. But first we have to deal with the resonant frequencies of the structure itself, and Actran helps a lot with this. So this is a classic workflow that we use to study NVH of an electric motor. We have first our finite element model, then we have electromagnetic forces, then we combine everything together, we compute the surface velocities, and with that we can compute acoustic radiation of the motor. And I used Actran workflow, so the workflow that Alexis was describing before, to compute the electromagnetic forces. It's very easy, pretty straightforward, and it saves a lot of time. How do we use it? So we have this workflow here. The first step is to introduce two mesh files. The first one from the electromagnetic design, and the second one, you can see it here, the universal file from the finite element model. So then you combine two. Actran is very smart, so it positions the meshes together, and then you can calculate the motor harmonics from your electromagnetic simulation. These motor harmonics can be exported later and can be used in Actran VI to compute the acoustic radiation. So this is what we did with this workflow. We computed the radiated power of this in-wheel motor. So you can see there are some resonances at different frequencies. What is great, also we can compute contributions from different structural parts. In our motor we have rim where the tire is connected, we have the rotor, we have the wheel hub, and we have the rotor cover. So for each frequency you can compute the contributions, and you can see which part contributes the load in terms of its velocities to this radiated power. And then we can go even further. We can analyze frequency by frequency. So for example, doesn't talk. You can see it, the red line here. We can analyze this frequency a little bit deeper. And what we see, we can compute the model participation factors at this frequency. So we have here different eigenmodes. And we will see that, for example, the light green and the dark green will contribute the most to this radiated power. And we can see them on the right side, which part of the structure is resonating. So we can see the contribution of the ring. We can see the rotor cover is resonating. So we know if we want to get rid of this frequency, we need to work on the structure. And it's also, it can be used for in-cabin installation, it can be used for pass-by noise. For example, we can see that the rotor cover will radiate more towards exterior. So it might cause issues for pass-by noise, but the ring will radiate more towards the cabin. So it will help us also to choose right insulating materials for our cabin. For pass-by noise, so the next topic is pass-by noise. And why do we need the simulations for pass-by noise? So you can see the history of pass-by noise regulation on the screen. And we went from 82 dBs in 1970 to 68 dBs in 2024, and this is our target. So if today we passed the homologation tests with 70 dBs, we were below 70 dBs in 2 years, it will be 68 dBs. So we have to be ready, we have to develop simulations, methodologies to be sure that we will pass this test, to get the vehicle on the road. So what is pass-by noise? You can see here, normally the vehicle will drive onto a track of 20 meters length, and the sound pressure level of the car will be measured by 2 microphones on each side of the car. Normally the vehicle drives at 50 kilometers per hour, and then the measured sound pressure level should not exceed a certain level, like 70 dBs or 68 dBs in 2024. How do we do it in simulations? In simulations, the vehicle does not move, but we have microphones on each side of the vehicle, and we will circulate over these microphones to measure the sound pressure level. So this is what Actran workflow does exactly, and we can see next the model. So this is our car. We can see the carb, we can see the tires, and we can see the acoustic mesh. For pass-by noise, normally in combustion engines, the main contributors are exhaust and tires. In our case, it will be tires, and it will be also maybe electric motors. In this case, the study was done only with tires. So you see the tires are represented with 2 or sometimes more monopole sources. And the biggest challenge in the study is to get data for the tires, because you probably know the suppliers are not so keen to share this data. So if you want to run a simulation with yourself with tire data, you will not be able to get materials, layers, velocities. So it's very, very difficult. But there is another way to do it. You can ask your supplier to measure by themselves the level of the noise and give you the data. So this is normally what they can do. So the next slide will be about how to treat this data that we get from suppliers, so this measurement data. So in our case, they measured the tire. It was an indoor measurement, and they placed 11 microphones around the tire. They gave us the pressure, amplitude, and phase for each microphone. And now what we should do in our simulation, we can reproduce the same setup in our simulation. So you can see here the tire, you can see the ground, and you can see 11 microphones here. And the goal of the simulation is to find the right number of monopole sources around the tire and the right distance from the tire and from the floor. So we start with 2 monopoles, we can go up to 10 or 11 monopoles, and we should also find the right distance from the tire. How do we do it? So there are 2 steps. The first one is we place in our simulation 2 spherical sources. Let's say we continue with 2 spherical sources, and then we use unitary mass flow rate, and we simulate the pressure in 11 microphones. As the source was unitary, these pressures can be directly treated as transfer functions, and it means we have the transfer functions. In this formula above, you can see how we compute the pressure at microphone 1. So it's a combination of transfer functions and source strengths. What we want to find the source strength. For 11 microphones and 2 sources, what we will have the pressure at 11 microphones, which is measured by the supplier, and we will have the transfer functions because we computed them in our simulations with unitary sources. So we can solve this equation, and it will give us an approximation of source strengths. And then the optimization will be about how to place them, how many of them we want. We did this with 2 sources, and you see that the results are not quite right. So we can optimize it further. So the red curve is the test curve for microphone 1 and 8, and then blue and green are simulations with 2 monopoles. Nevertheless, we continued with this data for our quasi noise simulation. And here, this is what Actran gives you as the result. So we have 2 sets of microphones on the left side of the car, on the right side of the car. So you can see left and right side, and you can see. So we have 2 monopoles times 4 tires. It gives us 8 sources. So you can see them listed on the left, rear right, rear left, front right, and front left tire. And on this bottom curve, you can see the total sound pressure level and also the contribution from every source. With this data, for example, what you can do, you can see that there is, in this middle frequency, there are quite some high levels, and then you can analyze whether it comes from your source or from your transfer functions. Actran gives you also transfer functions, and we can see them here. So at exactly the same location, we have the transfer functions, and we also see some high levels around this central frequency here and here. So what we can do with this data, we can work on insulation of our car. We can choose the right material for wheel arches so it can absorb the sound from the wheels. You need to have the frequency data for this. And also for under tray material, you can choose the right material with this data. you can rerun the simulation and you can see how it will influence your plasma noise. Yeah, so that was it for me. Thank you.